All right, guys, welcome. I'll give just a brief opening remarks. This is the first time we've run this tutorial. Kind of the motivation, if you read in the program book, the little description, that pretty much sums it up. There's a lot of great work at CVPR and academics and leading research labs. And what I found in the last few years after kind of transferring into industry was that there is a lot of work that goes into kind of packaging these algorithms, deploying these algorithms, writing kind of robust, what I'll call industry code style software around these algorithms to actually make them do something that's kind of sellable and is a real product and that sort of thing. So I thought CVPR kind of was missing some talking about this. It's a big part of what actually has to happen to make these algorithms kind of successful in the wild. So I kind of collected some people from some of the, I guess we can call them thought leaders in the industry about this type of thing, and we thought we could share some of our best practices and just show you some of the stuff we think about, and hopefully that kind of just helps you think a little bit differently as you're developing your algorithms. So just to set some expectations, this is again the first time we're trying to cater to a very diverse audience, right? Some of you probably are quite versed in software engineering, others may be pure academics. So we've got a variety of topics. I'll start off with a talk that's very much on the software engineering side. Some of them go a little bit deeper into the computer vision side. We'd love to hear your feedback afterwards. Stop us in the hall, let us know if you want to do this again. Just what you thought, how we can improve if we do it again in the future. So with that, we'll get started. All right, so you can read this mouthful of words here for the topic, but really this talk is about what I'll call frameworks. And whenever I start doing something like this, I usually like to make sure that the world agrees with my definitions of some words sometimes. So just go into a dictionary. What is a framework? A basic structure underlying a system. And that's really what we're going to talk about today, is how we can construct structures like this in our software in order to kind of accelerate some things. More specifically, what is a software framework? And here's the meat of what we'll talk about. An abstraction in which software providing generic functionality can be selectively changed by adding additional user code, right? And so that's really the key, where we're going to have some kind of core code, infrastructure code we'll talk about, that then you can take these algorithms and treat them as this specialization. And what do I mean by accelerating? Just in the idea that we can actually go faster overall by doing this, right? So if we don't do frameworks, we'll go some speed. If we do make frameworks, we'll hopefully go a different speed. All right, so again, why do we like frameworks? So besides the speed idea. So it helps to separate and focus responsibilities between people and teams. So I've got this little, I like these little cartoon pictures. I think they kind of give you some memory anchors here. Swiss Army knives are great, but if you want a big knife, that's not it. If you want scissors, that's not it. So kind of specialization is real. Some people are kind of jack of all trades types of people, but I claim that in any one thing, they won't be as good as the expert in that thing. So kind of trying to take advantage of that is what we're driving at here. Exactly that same idea for staffing, right? So as you're hiring for teams, as you're deciding with your current staff who's going to do what, being able to think about this in a kind of plug and play modular way is really important. Modular design of the software is almost kind of free once you get this kind of framework thinking down. As kind of a hobby, and we're all computer vision people, I'm into photography, and this kind of idea of a DSLR with interchangeable lenses is really a great summary of the idea of these frameworks, where if you have a camera body that's got this lens kind of mount on it, when you're developing lenses, you don't have a choice but to think about how am I going to plug this thing into the camera when I'm done, right? And that's what we're going for. And code reuse, we'll talk about that a little bit. That's really critical for maintenance, for testing. I mean, is doing the most things with the smallest amount of code that you can is really what I'll call a successful project. All right, so a little caricature, if you read the bottom here, just a caveat that this is all made up data and just kind of conceptual. But thinking about the success of a new team over time, or an existing team over time, if we kind of break down the work that's going into a project into two parts, right? It's clearly more than two parts, but a very high level grouping. There's the infrastructure, code and stuff and mechanics, and then there's the project specific stuff, the business logic, if you will, whatever specific detector you're working on. So looking at kind of a team who doesn't think in frameworks, and obviously this is overgeneralized, so if your team doesn't think about frameworks but does better than this, that's great. But in general, at the very first project, so project 1, you have to do a lot of this infrastructure stuff. You're writing I/O functions for different formats. You're thinking about how you're going to handle outputs. What kind of databases are you going to use? You have to kind of build all this infrastructure. And I've kind of arbitrarily said, all right, a little bit more than half maybe infrastructure, and then a little bit less than half maybe like the actual thing that you're doing, right? So if you haven't done that well, or modularly, or in a framework like we'll talk about, project 2 goes almost identically, right? You start some new thing, you're gonna have to go back and copy and paste code and kind of start making this project from scratch. If you have a different team doing it and you're not able to leverage what the first team did, you gotta just basically do the same thing. Project 3, same thing. Project 4, same thing again, right? So this kind of upper management guy up here, I'm saying, at the beginning they say, well, this team is okay, right? They're not doing anything particularly bad, particularly good. But then project 4, they say exactly the same thing, right? Your velocity is like constant. But by thinking about frameworks, the idea is, in the long run, you'll be successful, but you have to kind of eat this caveat at the beginning, where at the beginning you have to spend a lot of time thinking about this infrastructure, a lot of time writing this kind of framework code. And so you may get some pushback, right? They may start saying to you, hey, why are you going so slow? And it kind of takes a kind of strong person with a real pushback to leadership to say, hey, you know what? It's important that we get this stuff right. I promise it's going to go faster in the future. Trust us, right? So it's kind of a hard sell if the management's not into this software development type of thing. But hopefully very quickly you can start showing them that this is working, right? So project 2, we've shifted the balance a little bit. We're still spending a lot of time on infrastructure, but overall we're going much faster than we did the first time. But by project 3, project 4, now all of a sudden you can just do the work you're supposed to be doing, and you don't have to think about this infrastructure stuff, right? You've already got your mechanics of accessing your data and doing your evaluations and all these kind of things. You've got that done, working, tested, trusted, and now you just do the business logic, right? And so at this point, the management is saying, man, we need to give all these guys a raise. They go so fast. How did they do it, right? And so hopefully some of the things in this talk will get you to how do you do it. All right, so this is kind of the highest level I could think about how to think about these sorts of things. So, the least modular way or the least frameworky way to think about you're about to write some code, what are you thinking? If you say, all right, I've got this problem at hand, how do I solve it? Right, so just very, very kind of narrow thinking, saying I've got to go from point A to point B, it was the fastest way I can get there. The how do I solve this problem mentality, I think can very easily kind of accidentally lead to non-modularity, non-reusable code. These kind of things I'll declare are bad throughout this talk. Kind of step 2, the second level thinking is, instead of just how do I get from A to B, it's how do I get from A to B, but I'm anticipating some roadblocks, right? I don't expect this vector is actually going to be straight, and what can I do to help myself get to B quickly, right? So maybe it's something to the effect of what kind of parameters might I want to change, and we'll talk about this very specifically. But kind of even better is, what other problems might look very similar to this one that I can kind of pre-design for, right? And there's in software a principle called YAGNI that we have to kind of level set that sometimes is a good idea and sometimes isn't. It means you're not going to need it, right? So sometimes it's the concept of over-designing stuff. So you have to pick and choose where you do this, right? If you don't expect you're ever going to do anything like this again, then don't bother thinking about it as a framework. If you know for sure you're going to do this again, then you should definitely think about it as a framework. All right, so throughout the rest of the talk is basically 3 examples. The first one we go into very specific details about some kind of pseudocode and how you could actually think about the mechanics of some of these things. The second one is a little bit more abstract and thinking more about the actual pattern. And then the last one is just kind of reinforcing the idea. All right, so bear with me on this slide because of the diverse audience. I've got to go through this a little bit to make sure we're kind of all on the same page. I'm using this example that hopefully a lot of you know already, is the idea of line fitting using RANSAC, right? So we'll quickly go through this because that will help make the points on the next slides. So if you're not familiar, the idea of RANSAC is you've got particularly line fitting with RANSAC is you've got a point cloud or some set of points, and you want to find the best fit line in the presence of outliers, right? The idea is you kind of iterate until convergence. Here we've set some kind of max iterations type of convergence criteria. You're going to pick 2 points, you're going to fit a line to them, you're going to count how many what we call inliers are on that line, right? So the points maybe close distance to the line thresholded or something like that. And then you're going to just do that over and over and over until you want to stop, right? And then you pick the best one and that's the answer, okay? So, you know, this kind of half pseudocode, half real code type of code here, you can see, you know, there's a lot of kind of setup work. There's a lot of things that are very specific to this algorithm, right? Choose 2 points. We're going to return a line. The function's even called fit a ransac line. But then there's some more generic stuff down here. So just counting inliers, you know, start saving the best result, and then iterating, right? So this was how you think about how do I find the best fit line using ransac, right? This is how do I solve this problem? So you know, you may show your teammate and they may say, okay, right? Not impressed, 10 lines, not that exciting, right? So what you can do better, right, is say, okay, you know, I have no idea if 1,000 iterations is going to be enough, probably, right? So let's bake that in from the beginning. Let's parameterize this on how many iterations we're gonna need. So you're gonna use this maybe to fit lines on 2 different settings, or maybe 2D lines, 3D lines, something like that. You know, you may need a different number of iterations. And you may also not know how kind of broadly distributed the data is, so you may want to say, all right, what's the inlier threshold? So how close do I expect the points to actually be to the line for the points that do belong to the line? So, you know, there's no magic here, right? I would hope that this is what any sensible ransac line fitting algorithm kind of function signature looks like. But you can see, you know, we've kind of introduced a little bit of complexity at the expense of hopefully a lot of kind of extended use cases, right? So, your kind of colleague says, okay, yeah, that's cool, but I need to use a custom distance metric, and this doesn't let me, right? So how would I do that? I basically have to tear out the internal mechanics of this thing and write it again, right? So there's this copy and paste problem that we'll talk about more explicitly in a minute. So even better is instead of parameterizing on values, you can parameterize on functions, right? So this is the idea of functors or you know, function object types of things. Here we've passed a stopping criterion, so you could bake in that number of iterations to that function, and, you know, when you construct it before you pass it, and a compute inliers function. So very generically, you now have a ransac algorithm for line fitting still that can basically do whatever you want, right? And forgive me for oversimplifying if those of you who are really into this stuff know there's plenty of other things you can do with ransac. All right, so this time, your colleague says, great, that's a really nice implementation of ransac line fitting, but what I need to do is fit planes, right? So now what do, right? You're totally stuck. You have a function that's very, very specifically designed to fit lines. So again, just to drive this point home, what you absolutely want to never, never, ever do is do this. Take the line fitting algorithm, copy and paste it, and change all the instances of line to plane, change all the instances of 2 to 3, because exactly this problem. So right, the mechanics of the ransac algorithm here in red are literally going to be copied and pasted at the end. So you know, I call this a maintenance nightmare. So what do I mean by maintenance? If you find and fix a bug in your plane fitting algorithm, your line fitting algorithm will still have a bug. And kind of worse than that is now you'll think it's fixed, right? You say, hey, last week we fixed this problem. It can't be that. We're going to have to spend a lot of time debugging. It turns out you just had a copy of the same code and you fixed it in one and not the other. Right, same thing for improvements, not just bugs, right? Hey, I made this go 5 times faster. Okay, well, why is my line fitting still so slow? Well, we only implemented it for the plane fitting algorithm. You know, for kind of generic refactorings, so say you change the way you represent points or something, right? You have to do this refactoring times n, where n is the number of objects that you're fitting with ransac here. And it kind of more subtle but worse is you have to test all the mechanics of the actual algorithm for every one of the objects, right? So you have to check that it's converging the way you want it to. You have to check that, you know, anything that you'd want to test when you're just thinking about the one algorithm, now you have to test the n of them, and that makes your test code, you know, crazy bloated. Where if you kind of do this right, then you just test the mechanics of the algorithm once, and then you just test the properties of each of the object in the functors once. Okay, so the kind of conclusion of this first example is, how would we say is the right way to do this? Again, this is not real C++, so we haven't introduced all the syntax with templates and everything, but sometimes you don't have to, right? So in different languages, there are lots of different ways to do these things. Here, the idea was, we have this abstract model class. This could also be a template parameter of what kind of object you're going to return. We've kept the same idea of these functors here. We've also introduced this idea of choose n points instead of choose 2 points or 3 points, so that n can be a function of the type of model. This is on the slide not that much more complicated, but your team may be kind of divided on this, right? Somebody might say, hey, perfect, I'm a good software developer, I know all about templates, I know all about functors, this is awesome, this is exactly what I want, so that I don't have to ever think about ransack mechanics. But some of the team may say, yeah, but man, this thing looks crazy now, right? There's 6 template parameters and there's all these functors and all this kind of stuff. You have to think about your team, right? So if you have these specialized people like I talked about at the beginning, hopefully they're able to do this kind of stuff and contain the complexity, right? So you want your kind of experts, your hardcore C++ dev guys, let them write the mechanics of all this stuff, but also let them design good APIs so that nobody else ever has to think about this again, right? You don't want your research engineers kind of debugging template, instantiation errors and stuff like this. So there's a balance to be struck, but I think ease of use is a critical thing, but also enough complexity, kind of finding the balance of the amount of complexity that's warranted is really important. So just kind of diagrammatically, this is what you get when you build a framework. So this is kind of a very loose example of a framework because this is literally just a function. But what you have is kind of the framework itself. So here's this ransack estimator. It kind of takes a model functor, an inlier functor, and a criterion functor, and it produces a parameterized model, right? So this is the hyper-generic, high-level view of like, what does this thing do? Now for each of these colored boxes, now we have to write some options, right? So here are 3 choices for a model functor that we could have. I've just kind of taken the obvious examples here. Some choices for inlier metrics. You may have point to plane distance. It could be signed, it could be unsigned. Inlier criteria, you could threshold, less than, greater than, between a range, that sort of thing. And if you've done it right, your kind of algorithm guys can almost literally press a button and build an algorithm, right? So they hardly had to write any code. They just said, I want this, I want this, I want this, and then they got like a functional block that they can do something with. And that's kind of the power of this. So you have to not be naive though. You can't just say, hey, I've got this big geometry library and now, yay, I can plug it into my RANSAC framework, right? You have to consider like the technical details a little bit, and just as one kind of high level example, you kind of want, in this case, all of your models to kind of behave the same way, right? So you don't want a line class that needs to take a vector of points and a plane class that takes 3 points as the parameters for the constructor. So you need to do some more abstraction here. And in this case, the simple thing was, all right, let's just think about a parameter vector. In the case of like ax plus by equals 0 type of a thing. ABC, ABCD for a plane. That's your parameter vector. So you can say, all right, as long as we can construct your model with a parameter vector, so this, the signature looks almost exactly the same, and as long as you can get the parameters back out of the model and kind of in an interpretable way, now you can plug these things into the RANSAC framework, right? So in some languages, this is almost the concept of duck typing a little bit. This is almost just the concept of abstraction. You have a polymorphic class that takes this as the inputs. So these are important details that you have to really think about sometimes. All right, so how are we doing on time? All right, I guess we'll go faster. So just another example, this is a little bit of a higher level thing. We're not going to talk about code anymore this time. But for accuracy evaluation, we, at here at least, we like to think of this as a framework, right? So we're going to do some image-based object detection, and then we want to understand, perhaps the intersection over union. We want to understand some kind of hit-miss recall type of thing. We want to compute different sorts of precision and that sort of thing. And we're going to do that in 2D. We're going to do that in 3D. We're going to have all these different choices of different types of things we want to compute and different ways we want to write the output. And so that's what I mean here by an accuracy evaluation framework. And so kind of throughout this talk you may be saying, well, that's all nice, but how do I do it, right? So unless you have a big team of people who have done this for 10 years, like maybe you're not going to get it right at the beginning. So my advice, if I can be so bold as to give some, is kind of just write out the algorithm in kind of the smallest number of words and bullets that you can, that you're going to explain to somebody without any technical details, right? So what does it mean to evaluate an algorithm? You're going to load some data, right? Probably some evaluation data and some algorithm output. You might want to partition it. So, come from map making, maybe you want to do per road or per tile of the map or something like that. You need some way to compare two sets after they've been partitioned. You may want to produce a report, and then you probably want to store and kind of archive that report somewhere so you can look at it over time or something like that. So each one of these bullets just turns into a box in your framework, right? So you may have abstract some concept of like a data provider, a partitioner, an evaluator, a metrics, compute metrics type of block, and then a save the output type of block, right? So hyper generic. You'll also need this kind of magic orchestrator. We call it sometimes a runner or something like this that wouldn't probably show up in your list because you are the orchestrator as you're reading this list to somebody. But now you have a framework, right? Now you have a context in which to think about, now how do I get these kind of software mechanics right in order to make it look very much like this when I write the code. I kind of want 5 lines to be, how do I evaluate this new algorithm with one of our existing functors, right? I don't want to write thousands of lines of doing anything. So now what are the benefits in this particular case for accuracy evaluation, right? So one of the major things is we kind of jokingly but not really call sometimes what we do test-driven development for algorithms, right? Or test-driven algorithm development. And it's kind of a joke, from the software world. They have this TDD concept of, if you've read the books or watched the videos, right? Red, green, refactor. So the idea is you write a test that says when I'm done writing my code, this test will work, but right now it shouldn't, right? It doesn't work. Then you write the code, you make sure the test works, and you kind of repeat ad nauseum, right? So with algorithm development, you kind of often people will dive into the deep end and start going crazy writing some algorithm, and they haven't yet thought about, well, what's it going to take to evaluate this, right? So do I need some new evaluation data? Do I need a new evaluation kind of process or functions or these kind of things? So by having this evaluation framework and kind of requiring it to run at the very beginning of the development cycle, you get a very different outlook on how you're doing in the project, right? How many times have you started working on a project, you get 3 months in, and somebody says, how's it going? And you kind of say, well, pretty good. And they say, well, show me, like, what'd you do this month? And you don't really have any curves that are showing you, like, how's it going over time, right? With this, you start a curve at day 0, right? Your curve says 0% recall, 0% precision if you're working on detectors. 0, 0 is much, much different than nothing, right? If you don't know how you're doing, that's very much worse than knowing you're doing bad, right? So kind of everything we do, we immediately plug into this evaluation framework and kind of watch the curves over time, and has been tremendously helpful for us. Let's see. All right, so just another cartoon of this, right? So it kind of looks complex, and hopefully, you'll see the simplicity kind of materialize. We're at in the middle here. You've got the actual algorithm framework. So you've got some reference data provider, like your ground truth, your query data provider. This is your algorithm output. You kind of need to think about how you're going to load those things in memory. So you kind of have this magic middle layer here that we didn't talk about in the English kind of description of this algorithm. That's an important step, right? So you may not always want to store your ground truth data and your output from your algorithms in exactly the same way. So you need a kind of interface layer that says, hey, just give me a folder or a database or something, and I'm going to deal with giving it to you in the format that you're kind of expecting. So you can have different boxes here for each one of these things that you can plug in. Now, what kind of evaluation do I want to do? What kind of metrics do I want to compute after those comparisons are made? Do I want to trigger some different things with like an options class? And then how do I want to report this stuff? And down here we have the options, right? So again, this is what I mean by at the beginning. You have to write all this infrastructure at the beginning. Just because you write this cool framework doesn't mean you can do anything yet. It's just a bunch of sockets that you can plug stuff into. Once you have these big boxes full of options, that's when this really gets powerful. So here you've got your interface, intersection over union, your polyline distance. You can have a zillion different types of polyline distances. You can have area of overlap, not just intersection over union. So again, all you do is kind of choose which ones of these you want, plug them in. This whole thing should be like 10 lines, and then you get exactly what you want, right? So now you have this wonderful, clean-looking thing. All the interfaces are kind of already worked out, and you don't have to think about them. You can just stay focused on your problem at hand. And all right, to stay on time, we'll kind of breeze through this one, just getting to one last point. This one is hyper generic. We literally call it this generalized data processing framework, right? And this is not super generalized, as obviously you have to keep it a little bit focused on the business. But you know, we're often loading LiDAR, loading images, that kind of thing. So kind of have this like ultra generic concept of we're going to load some stuff, we're going to do something with it, we're going to output some stuff, right? It's very similar to the accuracy evaluation framework. But the reason for this example really is that it doesn't have to be just a kind of single-threaded type of, you know, one executable that you can build these frameworks out of, like it was in the previous examples. This algorithm box in this case, this is where kind of the magic happens. This can be a Docker image that just has a callable that people are expecting. It could be a web service. You know, it could be whatever you want here, and this concept still holds, right? So you can kind of go from the RANSAC example was like just a function that we've thought of as a framework. The accuracy evaluation framework was a collection of classes that we thought of as a framework, and this generalized data processing framework is a collection of callables that we think of as a framework. So here, you know, the concepts are you can get your stuff, your input from files, from databases, from web services. Your algorithms, this is what we at CVPR are focusing on, you know, like how do we detect signs, how do we detect polls, that sort of thing. And then the same thing with the input as the output. Are we going to write this to disk for debugging? Are we going to write this to the map? Are we going to write this to a database? So once you make a new blue box, you kind of push the button and you get what you want, right, with very, very little mechanics once those mechanics are in place. And the final point is, you know, coming back to the staffing idea, what we've done here is really, really let the researchers stay in the algorithm box, and we let the software developers stay out of the algorithm box if that's what they want to do. And by staffing that correctly, you can get that framework built kind of in parallel with your algorithms getting built. You can get that framework built probably much, much better than a lot of us as computer vision guys would probably do it. And it's kind of leads to success of the team, speed of the team, and all those good things we talked about at the beginning. So that was it. I hope you enjoyed the very first talk for the software engineering tutorial, and I'll take questions if there are any. There's a mic back there if anybody's interested, or we'll set up for the next speaker. All right, hey Ben. Oh, that's right. Yep, sorry. Get this out of the way. Thanks. That little thing is like a backup microphone. But yeah, okay.
All right, welcome everybody. First of all, thanks to the organizers for giving me the opportunity to talk about a topic that we feel is very important, not only in industry but also in academia. My name is Jan Ernst. I'm with Siemens Corporate Technology in Princeton. Just very briefly to my background, I have 2 decades of applied R&D experience in various organizations. Government labs, I've been in startups, and most recently in large corporate. I had an opportunity to get different perspectives as individual contributor, a project manager, director, as well as key expert, and I have experience in a variety of industrial domains, making things work in the real world. Very briefly, to where we are at the moment, Siemens is spending over 5 billion this year in R&D. 500 million of that is focused on a couple of topics that we feel are crucial for us in the future, spanning from cybersecurity over artificial intelligence and system autonomy. We have a particular strategy on how to go about that research. I won't go into too much detail. I think that's not super relevant, but this is the relevant part. The idea is that we start collaborating with academia to bring in the basic research, and then we mature technology until we create new business or extend existing business. This will become important later. Let me start off with a real-world example from CVPR to the real world. This is something that we built in Princeton. It's basically spare part recognition with mobile devices from RGB and depth data. And I will come back to this a little bit later. So let's start off asking how bad is it? And I'll just cite Nature. Did a review a couple of years back and figured out it's pretty bad. All right. This is across all sciences, but there is no reason to believe that it's any different for where we are. Dee Scully of Google used the term reproducibility debt, which I like very much. You should keep that in mind. What that embodies is that there is a cost associated with reproducibility, and cost is pain. So let's look, and I believe it's a hierarchy of pain, so let's look at that. And I'll keep track of the pain level along the way. So one thing that most of you are probably familiar with, this is the lowest level of pain, is reproducing another lab's result. This is already difficult and we're struggling with it, all right? But that's only the bottom layer, right? It's pain, but it's still good, you can tolerate. Then you do it on your data, that increases the pain. You're really starting to suffer there. And then you want to do it in the real world. This is where we really crank up the pain level. And then certainly you have to think in the long run, because we can't do one-shot things, but we have to look at the long term to really bring innovation into the real world. So that's cranking up the pain level to 11. So that naturally raises the questions, why do we make systems not reproducible from the start, right? So what I hear over the years is, there is no value. It's not my problem. I'll do it later. It slows me down. It's too hard. Yeah. So let's have a more structured look at these common objections. First of all, the value proposition. I'll just mention a couple of core values. There is much more, but that would need some more time. For the researchers among you, you will get confidence in results. That is very natural. It will enable sharing and collaboration, and we've seen this luckily in the community in the past 10 years more and more, that this is being taken serious, and reproducibility makes sharing and collaboration much easier from the start. You get more freedom of experimentation, for example, because you can take the risk of running another experiment, just wiggling a parameter here and there, because you know you can always go back to the previous parameter set that worked. For managers, just very briefly, it's a source of accountability, which is very important. In business, it'll be much easier to hand over successes in research to the development, and in general it ensures business continuity. So second main objection, it's not my problem. Yes, it is, or it will be soon. Let me explain. I'll go back to the technology lifecycle again that I showed earlier, all right, and I'll keep track of this. So you're young, upstarting, you have a great idea. Yeah, you do your thing. This is your core analytics module, and you get better performance on something, and you want to make business out of it, all right? So you have to go through the applied research, the pre-development, and so on, and you expect your thing to bloom into this pretty flower that will make money in the real world, just on its own, right? So let's look at how that works in reality, yeah? So again, you do your thing, and as you go from the research to the applied research, there will be another thing, right, that you have to do to actually make it work. And over the pre-development and prototyping, there will be more important stuff being added. And when you arrive at the business, there will be a complex set of dependencies that you're embedded in. Now, the problem starts when you do your next version of the thing, right? If you do not realize how you're embedded, and if you cannot do this in an automated and reproducible fashion, things will start to break very soon, and you will lose efficiency. You will still be able to get it done, but you will be later than your competitor, and you will have lost the race. Objection number three, I'll do it later, and you won't, and you know it, all right? So I'll talk a little bit about cultural and behavioral aspects of the topic because it's only partially a technical issue in a minute. Objection number 4, it slows me down. No, it doesn't. What slows you down is not being able to figure out what parameters you used in a particular experiment, getting some results that you just can't reproduce anymore, going back to some earlier graph and not being able to explain what exactly that graph means. What was the performance metrics? Did I really use only the manually annotated bounding boxes, or did I use semi-automatically annotated bounding boxes? And then you already have an issue and you have to go back, and that slows you down and you're done. All right. Myth number 5, reproducibility is hard. And this is the bad news, that is actually true. It's really hard. It's partially a technical problem, partially a cultural problem. The good news is that you'll be paid better, at least in industry, if you're able to handle reproducibility. If you come to me, want to get hired, and show me that you've done this successfully in the past, it's way more important than having good ideas in the first place, because making things work is more important. It's harder to do. It's harder to do, let's put it like this. There is a silver lining. Automation is getting there, and I'll give some insight, but we still need better integration. So you still have hard work to do. So now let me separate into 2 kinds of reproducibility that we typically look at. The first one is lab to lab. So you want to reproduce some analytics from some from your own previous results or from some other lab. There you typically ask questions like, can I replicate code, can I replicate data, experimental protocol, and so on. Then lab to reality asks more about, do distributions match? Are my priors good? Have I considered everything that I will encounter in the real world? All right, this is a less algorithmic perspective on reproducibility. In the lab you ask, can I replicate? The fundamental question for the second part is, when will it break? Because it will break, and that is very important to realize. And this is, if you take anything from this talk, then think about this question. Always think, when will it break? Because that will allow you to build systems that break less and are more robust and reproducible. All right, let me motivate the next section with a common sentiment that is being heard in the community more and more. 10 years back, we were handcrafting algorithms and code. Now we are modeling data, and we're still modeling algorithm, but a lot of what you see is modeling the input data to some algorithm rather than building computer vision pipelines low, mid, high level, basically. And I feel there is a learning in that. And to us, that learning that we've executed in the past is, why don't we treat data like code? That allows us to talk about interfaces, compositionality, semantics, and so on. I have a computer science background, so I'm happy talking about this. Once you realize that you can do this for data, you do the same for the rest of the experimental process and the development process. So you treat your reporting visualization, you treat it like you do code, and I'll explain a little bit how to do that and what it means in a minute. So let me take a structured perspective on reproducibility based on what I just said. So when you look at getting results, right, training a classifier, building a prototype, selling a product, you have all of these components that are there. You start with the code, then you have data, labels, you need to look at subsets of the data. You have your training workflow that tells you how to convert the data into a trained model. Then you need to evaluate, you have metrics, and lots of other ugly things that are components of getting results. These could be end results or intermediate results. And we just consider these basically as a cross product, all right? So it's a cross product of all of these components, and that gives you a result. Now, I feel there are at least 2 core elements to reproducibility. The first thing is, you have to have something uniquely identifiable. The second one is, you have to have it retrievable. Let me explain this on an example that everybody in the audience probably is familiar with, which is code. All right? So uniquely identifiable, you already have the Git hash. Yeah? There is no excuse for not being able to reproduce source code in times of GitLab and Git hashes. yeah, that maps a particular piece of code uniquely and unambiguously to a hash. All right, everybody's already familiar with this. Even if you're not realizing that this is what is happening in the background, you're already using it. And how to make it retrievable is just GitLab or GitHub if your organization doesn't have internal tools. So now if you think about parameters, right? Why don't you do the same thing, right? Instead of having them on your hard drive, some text file with some parameters, put them there as well, and bam, you have better reproducibility already. And then it's a very minor step to think about all the other components the same way. Yeah, you can do a git hash for the data. Certainly things become a little bit more technical when you think about, for example, terabyte-sized data. Yeah, that may not work very well with a git hash. You have to think about how to get the identifiability and the storage there. But there are solutions, even at a large scale, to address this problem of retrievability and identifiability. Now let me build on this and show a particular or an example workflow, yeah, of how this could look in the real world. So what do? You start with raw data. Let's say we already are able to address the topic of identifiability, right? You put it on GitHub or on your internal data store and you can identify the raw data. So this component now has a unique fingerprint, yeah? Then you express the subset of the data in a similar fashion. You assign it with a fingerprint, and now the composition of those two give you your data slice. So now this is the input for, let's say, your training system. And that has an inferred or deduced ID that is already uniquely identifiable just by the composition of the former IDs. And then you certainly want to have some ground truth data, so you have labels, you put them through the same slicing, you get your label slice also uniquely identified. Then you add data augmentation, and certainly it's important to realize that the data augmentation you also have to put in a uniquely identifiable fashion with similar methods. And the composition of that gives you your training data, you add hyperparameters, your bootstrapping protocol, and then you have a trained model. Yeah? Now, if you look at this, this is basically a directed acyclic graph. It's nothing more. Yeah? And this is the way to understand, or this is one perspective on how to understand this experimentation process in terms of reproducibility. This is very important. What that gives you is concise propagation of identity, for example. This is already, you can use graph theoretic algorithms to propagate identity and recover identity. And it gives you a lot of other benefits in scaling things up in the real world. You can compose, you can optimize, you can cache, depending on the scale and distribution of your workload, right? In academia, maybe you have a smaller lab, it's not that important, but in industry, you may have a global deployment of how to run these things, and then you have to have, then it helps to have such a structure. So now you have this, you have a trained model, and the beauty of this is also compositionality, as I mentioned. So now you make this with its unique ID that you already have, again, component, right? And you add a validation set. And that gives you validation scores from the evaluation. And then you add your performance metric, and then you get the end result. Yeah, so you also have this, via the graph structure, you automatically get things like hierarchical descriptions and models. And now the beauty of this is, yeah, you have this ID, and it's really, it can be as simple as just a hash. It can be just an SH81 or 256 hash, and it's uniquely linked one-to-one with the end result. So when one of my guys comes and shows me a result, yeah, and then I want to see, okay, this looks great, we are beating the state of the art. Give me the hash, and I can reproduce. Yeah, end to end, including training, evaluation, unambiguously, no matter where I am. Yeah, and that is what gives you efficiency. This is what makes you efficient. All right. There is a lot of need for tooling to get something like this done. The issue that I have a little bit is that this depends on your organization, right? I'm just gonna show a couple of obvious tools and mention the main things that you need, but how to do this in practice depends on your organization, what you already have and what you can afford. But in general, you should look for reproducible source code tooling, which is already there and everybody's familiar with. You can also think about reproducible development environments. This is becoming more and more easy, even without paying a lot of money, things like Docker and Vagrant. Reproducible infrastructure is also there by now, so if you're concerned about a distributed learning scheme and you need a lot of machines and how's that reproducible, this can be done by now. And you just make sure that the way that you pull up your infrastructure via Terraform, for example, is also embedded in the graph so that you can reproduce it. Then there are, I'm happy to see that there are more tools coming up that specifically address that problem of modeling ML pipelines such as data version control, Studio ML, and so on. And then certainly there's the old school kind of automation from software engineering, like continuous integration. I'll just mention a couple of things to do and things to avoid on the coding level. So if I see somebody using the command line excessively, right? They start the training process and they start their the data pre-processing pipeline and so on. Then I have to ask, can you really reproduce that? Yeah? So keep that in mind. By now, there are excellent tools where you can do something similar as you did on the command line without the drawbacks, things like IPython. And the most recent Jupyter lab gives you a much better handle on interactive data exploration without losing reproducibility. A very old school topic, certainly don't hard code. That kills reproducibility. One topic that always comes up when thinking about reproducibility is randomness. So a very basic thing is to make sure that you have deterministic randomness, use random seeds. Yeah? And that can be done throughout most code and most libraries. Sometimes you get in a place where you have a third-party library that for some reason is non-deterministic random and you can't influence, particularly with a newer set of libraries and tools and GPUs that comes up once in a while. That is certainly a tough bet. Yeah. All right. One final slide in this part on best practices on data, and I saw some of these ideas reflected in David's talk as well. One of the best ways to ensure reproducibility in data processing is not to allow direct access to the data, but instead only allow access through interfaces that have unambiguous semantics, such as lifetime and so on. There are good interface definition languages, and I expect in our domain for this to come up more and more in the future, hopefully standardized ways of talking to data that allow you automatically to separate the meaning and the representation of data. So for example, let's talk about pose, right? You get a text file with a matrix or some numbers in there, right? That's a representation of the pose. But we need to understand the meaning of the pose, right? So let's, for example, the example of Euler angles, right? You get the angles, yeah? And then you assume, basically, this is your representation, and then you build the system, and then at some point it breaks, yeah? And this is because you were using a right-handed instead of a left-handed coordinate system, right? This is part of the semantic that we may miss. So you don't talk directly in Euler angles, but unambiguously say, I want to have it in this representation, and leave it to the interface and API layers to convert it to something that is up to your specification, basically. All right, couple of best practices. I'll go just through this very briefly. On cultural aspects, you should start early, realize that reproducibility is value and not a nuisance. Take ownership of this, understand that it's your problem and everybody's problem, also as a group. And managers should incentivize reproducibility behavior in order to improve the overall outcome of teams. All right, now second part, let's talk about reproducibility in the real world. And I'll motivate this with an example of our past to highlight a very important point in reproducibility in the real world. This case study is the World Expo 2010 in Shanghai, where we had the opportunity to provide for one of the pavilions the technological centerpiece with a lot of exposure, right? You're talking tens and hundreds of thousands of people over 6 months. So the objective for this was to build a collaborative 3D real-time natural gesture interaction system. We built a nice thing where 3 people together could build a car in 3D with autostereoscopic visualization and the whole brimborium. This was pre-Kinect, right? So we had to do the analytics. This was some probabilistic boosting tree stuff, but we also had to do the infrastructure up to the set design and hardware, certainly. So the challenges there were, we had 4 months to build the system from scratch, design, build, and test in Princeton. We were planning for 5 days setup in Shanghai from beginning to start, so we had to hand over after those 5 days, and then it was supposed to run for 6 months uninterrupted, without any kind of technical expert on site, with a one-button operation, turning on in the morning, turning off in the evening for half a year. So we started off, we built nice UIs, we built the analytics, a lot of engineering, and then in the end we had a set design. So this is what we were expecting on site, a very nice spaceship-like thing. So then we come on site 5 days before the go live, and this is how it looked. Literally half-finished buildings. Yeah. I already recovered from the initial shock here, but this was quite something. So we started off with the drywall around us, the dust coming off, and power from a generator. And then you're talking calibrating cameras, yeah, and testing systems and looking at illumination, making sure that things work. 5 days. Yeah. All right. So what is the issue with the real world? Yeah. And I'll take a Bayesian perspective on this. The issue is, first of all, your expectations. Yeah. Your expectations of what you encounter will be either incomplete or incorrect. It's always either of the two. I have not seen a system where this is not the case. You're always missing something, or you're always slightly off. This is very important to realize. And the other is the data, that it is scarce and biased. This deserves its own workshop, so I will focus on the prior topic. I'll just mention very briefly, because most of you are very familiar with this, that there is a lot of assumptions that you can make about the real world, right? Illumination is a typical thing, and then you have a lot of other things that you have to realize that are there, and you're making assumptions on them, even if they're implicit. If you code an algorithm, you can already read off what kind of assumptions is this algorithm making on the real world. And reproducibility in the real world basically means being good in your expectations. So how do we make sure that it works in the real world? I feel there is not a structured way to do this. This is more an art, as I mentioned earlier, than anything. But I feel there is a bunch of things that you can keep in mind that will help you be better. As I mentioned, assumptions will kill you. Yeah. So the assumptions we made for the earlier example was that there will be a building in which we can install our thing, right? Turned out it was not quite there, yeah? But certainly we are talking more about priors, illumination, and so on, all right? If you make your assumptions explicit, make them qualifiable. Qualifiable means that you can go out there and test them fundamentally, right? An assumption that cannot be tested is not meaningful. Think about mitigations if the assumptions are not met. This may seem like a futile exercise, but if you think about mitigations, that will also force you to think about your algorithm, right? How will it work if this and this happens? And you will gain insight from that. You will gain insight from that. Certainly you have to do perturbation studies. That's a simple thing to do once you realize your priors. Just study how sensitive you are, not only to the hyperparameters, but to any kind of parameter that you have in the system. And then the best advice, again, repeating from earlier that I can give, is try to break it. Yeah? So let me just very briefly, for the sake of time, go back to this example and let me talk a little bit about a concrete way that we made this more reproducible. This is based on learning from CAD data and recognizing with a depth sensor. All right, so during lab time, we didn't know what kind of sensors would be there in a year down the line because it's developing very quickly. So we just spent a lot of time on modeling sensors and modeling depth noise and so on. So we built up sophisticated tools to simulate noise in our pipelines. And we built them in a way that we could factorize out certain things like having a structured illumination instead of a time-of-flight sensor. And that enables us later on to quickly react to get things done in the real world. All right. So going back to this, after this happened, it actually turned out that we were able to make it do. After 5 days, it looked like this, and we had everything set up. And it actually ran for 6 months uninterrupted, with only one hardware breaking down due to heat. All right. So there is a bunch of further challenges to reproducibility, things like experiment survivorship bias, but I'll skip through these very quickly for the sake of time. Just on the first point, experiment survivorship bias basically is you sitting there, running experiments, changing hyperparameters until it works, all right? And only the best experiment survives. And that is bad practice because you're losing all the information that you're getting from the non-working results, and you're doing manual hill climbing. So you may not generalize as well. All right, so finally, I don't know how to ensure reproducibility, but I'm pretty certain on how you get irreproducible results. Don't write down your assumptions. Yeah? Ignore the sensitivity to parameters and ignore bad results. Produce intermediate data that is not identified uniquely and copy it somewhere else or share it with somebody. That kills reproducibility because of the arguments mentioned earlier. Mix representation and meaning of data. Again, bad practice because you may have a different interpretation as somebody who uses your system, and then you're done. And finally, excessive use of command line. So, thank you very much for attending the talk. I'd be happy to answer any questions. Otherwise, you can also catch up with me later or pitch me an email if you're interested in a particular topic. Thank you.
So a lot of those things will work really well internally, like to a corporation like this. When you try to make it publicly reproducible, so number one, you don't always want to share your data sets. Number two, that cloud infrastructure you talked about, hardware you talked about,
Right.
not necessarily going to have all that
Right.
accessible. So how do you think about kind of scientific community sharing versus inside the corporation?
Right. So the corporate aspect is one thing, and there is very little you can do on a technical from a technical perspective, right? What I hope for the community is that we will jointly move more towards this kind of thinking. And as you've seen in one of the earlier slides, the first open source tooling, right? These are all open source tools are popping up to address exactly that problem, right? Even down to the line where you can have an automatic capture of your command line, right? And you have this shadow, this guy shadowing you virtually, looking at what you do on the command line, and then automatically making that reproduce. So all we would need to do is to foster these tools by using them and showing that there is benefit to the overall vision community. And then I think they will become more adopted and appreciated as well, right? A lot of this is about appreciating the value of this. It could be that we are going towards more standardization, perhaps, yeah, which is always tricky, so that we have a standardized way of expressing workflows that may be driven by corporate, yeah, and NVIDIA and their peers have a lot of tools. Right, thank you.
Good morning, everyone. My name is Ben Cadlick. I'm an engineering manager at Uber, working in the area of maps. So today for my talk, it's going to be kind of a nice follow-up, I think, from the previous talks. I'm going to talk about some engineering challenges that we have in the area of building maps at Uber. Specifically, this is a computer vision conference. I'm going to touch on sort of some of the imagery-related challenges that we deal with, but the general focus here is going to be about things you don't hear about a lot in the periphery of computer vision related to sort of scaling techniques, scaling approaches, and I'll describe some of the solutions that we've sort of come at to solve those things. But yeah, the focus here is going to be on some like very practical sort of things that we've come across, and just sharing it with an audience like this I think is hopefully going to be really interesting. Yes, I'll give a little background on some of our mapping efforts at Uber. I'll talk about some of these software engineering challenges that we have in the area of maps. I'll sort of scale these challenges to sort of computer vision at a large scale, and what are some unique things that we've come across in this space. And then I'm going to spend some time talking about active learning a little bit too. So I think active learning in our world is actually like very much an engineering challenge, and sort of doing it well requires a lot of sort of software workflows and things like that. So I'll spend some time talking about a lot of the practical applications of those things. So first, just to give a little background on sort of the problems that we're trying to solve here. We're using computer vision to help improve maps for both ride sharing and self-driving. These are the sorts of things that we're trying to map. This is just sort of a very high-level slide intended to show we deploy camera systems into the world. We look for things like traffic lights, traffic signs, addresses, road lanes. This is all the sort of stuff that we're trying to map out at a really large scale. And the thing that makes this sort of a difficult engineering challenge is sort of doing it at a large scale and sort of solving this problem everywhere in the world that you're operating. A little more background on sort of this effort. I think we have an interesting history, my team, and I like to share that with everybody. We used to be part of Bing Maps, so we used to build maps at Microsoft. We became part of Uber through sort of an internal acquisition at one point. And over the last few years, we've sort of been scaling up our mapping efforts and slowly trying to transition into things like online mapping and refresh. And so a lot of the sort of examples and challenges that I'll sort of be talking through today also sort of reflect this this sort of journey that we're on as a team and as a company as well. So first, to kind of motivate sort of some of this scale of this problem, and hopefully this sort of helps give you like a little bit sense of some of the things we're trying to get around. So like we went through a really big initiative a while ago where we've been mapping every single sign in the whole country. This requires processing some hundreds of petabytes of imagery, dealing with millions and millions of different sort of computer vision derived observations of some of these map objects, and doing it across hundreds, in this case like 200 different types of things that we care about. And so like doing this on a small scale is actually like not super, I mean, it's hard, but the real challenge that we face is sort of doing this at a very, very large scale. And there's some interesting challenges there. But first, let me give you a little bit more detail on how we go about doing this. And I'm going to sort of talk about the how in terms of like a platform. We have a lot of different camera systems that we'd like to use for improving maps. And these camera systems sort of come from different backgrounds. They have data in different formats, but we want to be able to leverage them all for the same purpose of sort of improving this map data like I described. So the first step in this process is sort of thinking about this problem as a platform, thinking about the different aspects of this platform. And some of those aspects are being able to just store imagery in a common way, being able to serve this imagery to a variety of tools or algorithms, be able to do training on different types of imagery, and as well as sort of large-scale inferences on this data as well. So I kind of break the problem down into a few different phases here and a few different steps within those phases. The first one I touched on a little bit already, collecting images. I think that's pretty obvious in general how that works. Some things that are a little less obvious is sort of what do you do after that imagery comes into your data center. So like some basic things that we spend time thinking about is, well, you want to be able to tag these images with some unique IDs. You want to be able to store some information with these images, such as where in the world was it when this image was collected? How do you like precisely represent this pose the direction the image is looking in sort of a global coordinate system. How do you keep track of the type of sensor that was used for it, the version of the sensor, the software that was running on the sensor when it was collected? And then how do you take all these petabytes of images, store them sort of in a geospatial manner so that you can quickly query them and pull them up? So these are some sort of like big challenges that you need just to be able to sort of do this type of work. Labeling, I think, is sort of a little more well known to this audience, especially attending like a CVPR like this. And training is sort of similar. So we train CNNs. We have tools to do labeling. I'll spend a little bit more time on talking about that, but also talking about it in terms of an active learning workflow. And then sort of some other interesting challenges are doing sort of large-scale offline inference. So how do you process, you know, tens of petabytes of imagery? Where is that imagery stored in the first place? So we use things like HDFS, block file storage systems to sort of be able to distribute this data in a way where you can take Spark pipelines and run inferences at a really large scale. We spend a lot of time actually just making this stuff work really well and making it work really efficiently and making it work fast too. So that's kind of the first step of collecting images, running CNN-based inferences on those images, and then storing the results in some data center. But to really get to a map, you have to start to think of things in sort of a 3D geospatial context. And that's sort of what these slides are describing here. So the first thing to think about is, let's pretend you've run some CNN, you've detected some signs in the world. You want to put those signs on a map eventually. So the first thing you do is you sort of take advantage of this pose information that you've stored with the image. You sort of cast a ray through this detection that you saw, and you sort of plot all those rays in 3D space, and you try and find where they intersect and triangulate. And you can further take advantage of things like classes of objects that your CNNs are recognizing. So maybe you see some stop signs, you see some yield signs, only allow those rays to, intersect, for example. And then eventually you can kind of create these map objects where you're like, yep, I'm pretty sure there's a stop sign here, maybe there's some sort of a caution sign here. And, but if you want to be really certain about it, you need a workflow to be able to put this in front of a human and say, hey, this is really important that we get this correct. Can you please confirm that this is something, because it's really important for us to get this right. So we involve humans in the loop a lot here just to make sure we have a really high level of accuracy on the things that we're putting into our map. And then the final thing is you sort of, after you're sort of working with this data in a incomplete state, you finally want to publish it so that other people can use it for downstream purposes and sort of rely on it as being at a very high quality, and then be able to update that as well as the world changes. So a couple of sides here I'm going to go into, and this is sort of all still the high level overview. Then I'm going to talk about some a little bit more case study type examples. But you need tools to do any sort of computer vision in this space. Our tools aren't super complex, really. We have tools that do detection labeling, that's basically drawing boxes on things. Tools that do classification labeling, that's saying, hey, what type of sign is this, for example? And then tools that we're working on that sort of let you do more of the map-based labeling. And this is the idea of, you know, how do you actually make sure this object is in the right location on the map and that your triangulation part worked well. And at a high level, the way that I think about these tools, especially when you're trying to automate something, is that they sort of should match some of one of your automation techniques that you're trying to do. So we have a detection labeling tool that's trying to basically mimic our object detector. We have classification labeling that should produce the same output as our object classification task. And similarly, this map-based labeling concept eventually should be able to produce the same output as what our triangulation is doing. And the goal is to sort of have these things be somewhat interchangeable. So if you have a really good object detection algorithm, you might be able to skip some human labeling step here. But maybe the classification part is still unknown, and so you can insert a human operator into that workflow to sort of fill gaps in your ability to automate things. And yeah, so this is just sort of a visual giving you some of that comparison between human tools and sort of automatic computer vision based tools, and how they can sort of, like, there's somewhat the same thing if you structure your workflows correctly. And it also starts to blur the lines a little bit between what is labeling, what is automation. They kind of start to become the same thing if you think about it in the right way. So just some other things that you sort of have to do when you're working on building maps at this scale is you need tools, you need an ability to sort of explore your data. We've spent a lot of time as a team sort of putting these sort of things together. It's been really useful for just being able to debug issues, to be able to sort of investigate and come up with new ideas for things that you can do with your data. And this is stuff that it definitely doesn't come for free either. Like a lot of time is spent on sort of putting together these tools that you can query computer vision derived data, and we've sort of gotten a lot of value from this sort of stuff. Some other high level things, and this is like actually really a good software engineering thing I think for people to focus on, is as we've been scaling this platform that we've been building, we've run into some problems. You know, we've had people land code that introduce bugs, that breaks things, that cause our data to look worse, and we sort of learned from a lot of those mistakes that we've made as a team, and we've sort of built some good software engineering principles around it. So some things that we do today, we have some continuous integration systems where, for example, we're working in Git, you land some code to our master branch. As soon as that happens, we kick off a continuous integration job that literally runs some data through a pipeline with some expected result, and it produces some precision recall curves against a known truth set. And so it lets us track as soon as everyone's landing code in the same area to make sure our metrics are at least not going down and hopefully going up over time. And being able to monitor this with a large engineering team is really important, because lacking this, you know, you might think unit tests are passing and some other tests that you've built are passing, but this concept of integration, when you have a really complex system, things get lost connecting these different pieces together. And so we've found that it's really useful to have sort of this concept of a more end-to-end type of integration test, and we've been able to catch some interesting bugs that way. Other things that we've had to do is monitoring for our pipeline. So I described these pipelines we have that sort of process really large amount of data. Sometimes we have deadlines maybe we're trying to meet where these pipelines have to be running really well, and we can monitor the health of these pipelines, which is oftentimes based on the health of our data center, and to make sure we're hitting goals where, let's say we need to be processing 20,000 images every minute. You know, that's what this graph here shows, and just making sure we're maintaining that rate, and also having a system where we can set alerts on that, where if all of a sudden our per image processing rate drops, you know, engineers can be notified, they can look into the issue and sort of make sure that our engineering processes are moving forward. Yeah, not like super sexy stuff here, but this has actually been really important stuff to sort of keep our team moving in the right direction. So now I'm going to spend some time talking about sort of some what I think of as like lesser known challenges in the area of building maps from computer vision, and this particular section here is going to focus on some things we do in the area of triangulation. So you probably remember this high-level overview I gave you earlier of how we go from something detected through computer vision in an image and how you turn that into a map object. So the perfect world looks like this. It's beautiful. Everything works great. Yeah, the reality is very much different from this, actually. So this image on the right here is, I think it's all of the observations we've had of no parking signs in San Francisco from a certain camera system that we have. And it's very complex, so to sort of think about this, just if you're top down looking at this data, if you were asked to sort of put a point wherever these rays properly intersect at something that should be a sign, like you're gonna have a really hard time. Why does this happen? You know, why isn't it so straightforward? Like there's a lot of like hidden complexity in some of these problems. So everyone knows that camera pose is often wrong, and depending on the sort of camera system you're using, that pose can be better or worse. But when you don't know exactly where an image is and you're trying to do sort of structure from motion type approaches to correct that, you still end up in cases where the world is not perfect, and you may, for example, triangulate a stop sign here a little earlier than its actual location, just because these rays intersected perfectly here, and every other sort of image-based signal you had said, yeah, I think it's right there. And this is also assuming you're working in a space without any depth sensor too. So you have no LiDAR to lean on, you sort of have some coarse ability to estimate depth, but it makes this challenge actually very difficult, and we spend a lot of time on these sorts of things. Similarly, on freeways, you have really large signs. You're detecting them from really, really far distances. You're also detecting them hundreds and hundreds of times, like 500 times. You might just see this one set of freeway signs. Also, your kind of sign detector may not get a perfect polygon around this object either. And so as you sort of cast a ray through it, based on how well that polygon reflects the sign, like if it's a large sign, that ray can shift fairly significantly. Yeah, so these are challenges that we spend a lot of time on, and I think some ways that we've been able to make progress in this area has been sort of like using frameworks a little bit to sort of reuse this term from earlier, but designing our code in a way where you can easily experiment with different approaches. So like, you know, one person has a triangulation algorithm that uses some certain image features, for example, another triangulation algorithm over here, and we want to compare them and figure out which one's actually better. This has actually been really challenging for us as a team because a lot of the issues we face, they're data dependent, and that data can be like a city, for example, and that city may have been collected with a certain type of camera system that had a certain type of error that we're trying to track. And so we often get into this game of whack-a-mole, at least as I call it, where you think you fixed a bug over here or a data regression issue, and then it pops up over here, and you can't really keep track of these things. And so people on my team have actually like spent a lot of time thinking about this and have sort of come up with a way to unit test algorithms like this based on real data examples. And that's kind of what this table here is trying to show. So this is just some example of one of these tests that our team has gone through. So what the rows here describe are different unit testable data sets that represent real data. And then the columns here are some different software releases that we're testing against that. And so this is just sort of an example, but you can say, all right, green, you know, this one's, it's doing better than the baseline. Red, it's doing worse than the baseline. And it sort of lets you evaluate in whole whether you're actually making progress forward based on real data examples, which is something that's, in the space that we're working in, we found it's actually difficult to sort of do it in small unit testable examples when you're trying to sort of address issues that are more systematic and more sort of, yeah, system level rather than like very small unit testable things. Okay, so I'm going to shift a little bit here, quick time check. I'm going to talk a little bit about how we've used this platform that we've been building to be able to do active learning in the context of road signs. But first I'm going to talk about some, again, like not really commonly addressed challenges in these areas. The first thing is labeling taxonomies. This is another thing that our team spends a lot of time on, is representing the signs and all the things that we want to sort of extract in the world in a way that properly represents potential variations between classes, also represents classes of things that may look different. So for example, like a one-way sign here, that looks different than a one-way sign here, but they still convey the same meaning. So sort of creating some hierarchical representation between these different things. And then also represent variations that exist across cities, states, and countries, right? So you might have a highway sign. This is a Texas catalog, I can tell right now, because there's a highway sign for that right here. But if you move to another state, that class of sign is going to look completely different. If you move to another country, like a large number of these things are going to be completely different. So how do you build a taxonomy that can adapt to these different regions? It is something that takes a lot of thought. It takes a lot of iteration, and it's yeah, it's something I would say that we still haven't completely solved yet either. And some reasons for it are, I guess, yeah, maybe not reasons for it, but some other challenges that you may not think of are, think of bus stop signs, for example. Every city in the country basically uses a different type of sign for this. And so if you're trying to build a classifier that knows what a bus stop sign looks like, you have a really difficult time generalizing across this class. Similarly, there are other types of signs that are just unusual, rare, and sort of time varying. You can't rely on them being in the same location for a very long period of time. We talk about these in terms of construction signs a lot as a good example. I tried to find some unusual, we have actually a lot of unusual construction signs that appear, like men working and things like this. But there's actually a wide range of these that are really hard to collect labels for. So how do we sort of use active learning and use some of the platform things that we built to make this better? I just described previously that we have this concept of a sign detector. It understands what a sign is, and really not much more than that. And so we leverage that actually to try and find signs that our detector knows, yeah, this is definitely a sign, but our classifier is like, hey, I haven't seen this class before. We call that an unknown sign, and it's sort of given by this sort of magnifying glass label here. So we can start to identify a lot of these objects and send them to humans and say, hey, like we're finding things that our algorithms don't understand. Humans, hey, can you reclassify these for us? They say, yep, that's a roadwork ahead sign, and from that we can then retrain using these things that are now labels in our world. So yeah, this is just kind of a very basic active learning workflow. We've sort of tried to further automate this by the fact that we're continuously doing labeling and continuously doing QC on our data with a large operations team that we have. We've built some automation that allows us to pull these labels weekly, daily, prep the data so that we can do some GPU-based training on them, be able to automatically spit out metrics based on these jobs that are sort of kicked off automatically, and then be able to actually version the model that's been trained too and push it into something like a model store that has a date on it, that has a reference to the data that it was trained on. So this is a loop that we've actually spent a lot of time on trying to build, and it lets us sort of keep progressing in terms of managing computer vision models and managing models that are changing against different label data. So what's kind of the effect of this? This is sort of some example data that I pulled and sort of added a little bit of stuff to give an example of the progression of active learning in a space like road sign classification. These graphs here, there's sort of 3 different time periods. Oops, I revealed too much. The vertical axis is, let's say it's 200 classes of signs. Horizontal, we're saying the accuracy. So highly accurate on the right, like no accuracy at all on the left. We measure this by using automation and then also asking operators to sort of verify some of these things if the automation was right or wrong. So I guess you can see over time as we go through active learning, a lot of these classes that had very little automation like slowly move to the right and slowly get more and more automated. But there's some nuances here that I think are really interesting, and that's what this slide is going to try and describe. So when you start off, let's pretend you're going to do this for the first time ever. You'll just do some random sampling. You'll randomly collect images across the city, and you say, hey, I'm going to try and get all the signs. You're going to get a lot of stop signs. They're common. They're pretty well distributed, and your classifier is going to do pretty well on those as well. And so active learning doesn't have a huge benefit on some type of data like this. Construction signs are a little different. So maybe your initial random sampling, you didn't collect any of them, and so the classifier has no knowledge about what this thing is. But through active learning, you're able to kind of pull those out and curate them, and they look sort of consistent too. They're these orange things. The classifier can learn it pretty well, and eventually you can get to a state of being able to classify those fairly accurately. And then you come to our friend, the bus stop sign, right? So the bus stop sign is the perennial challenge. Like, they're a little more common, but still with random sampling, you may not collect a lot of them. If you're doing training tests against different cities, your classifier just may not do well in that test city because those signs look different. And so, this is sort of a challenge that continues to exist, where objects that you're trying to generalize in this map platform, they may not generalize well across city and across the areas that you're trying to map. And so I'd say in many areas, like the bus stop problem is not solved yet, and there's some more creative ways to go about solving it for sure, but I think hopefully it sort of presents how active learning can be used in this case. All right, a couple more minutes. I've just got one more section I'm going to go through here. Last thing I'm going to talk about is some cool things you can do after you've platformized your work and after you've collected a lot of data around the world, and how you can actually use that to sort of accelerate human labeling or almost replace human labeling through some semi-automated approaches. So again, let's start from the point where we've found all of these signs. These signs have 3D locations, they have normals, they have bounding boxes in some cases. They've been QC'd by humans in some cases who've looked at it and said, yay, this is the thing we care about. Doing this at a large scale gives you a ton of data. And one thing that we've been spending time on now is like after doing all this in an offline sense, we'd like to see if we can leverage this data to sort of help improve some online or some real-time algorithms so that we can do this much more quickly and maybe it ceases to become an offline problem at some point. So again, we have some data like this. How can we further leverage it? Well, the first thing we can do is we can sort of collect data that approaches one of these objects. So let's pretend our goal is to actually be able to stop when we see a stop sign in real time. Well, we've collected a bunch of map data at some sampling frequency, and we've done this for millions of these objects across the country. So let's sort of start with this representation of some data. The next thing is we know this physical location of where this sign is. We have an approximate location of where we think this camera is that saw this sign from. And we can really just sort of back project the location of this object into the image and sort of produce an estimated location for where we think we should see this object of interest. Yeah, and then you can take a different set of images that go through the same region and sort of do that, and you don't get a perfect estimation for where this object is, but you sort of start to estimate the location of, you start to sort of get some approximate pseudo-truth labels for where this thing is. And yeah, I think that's kind of like the ultimate thing that we're trying to do here using this platform is you can take this huge map of data that you've collected, you can take sort of these 3D locations. If you have your imagery stored in a way where you can easily sample it across this map, you can create some really cool algorithms that do time varying things across this data that have more labels than you could ever possibly need to detect these objects, and that's sort of an approach that we're spending time on right now. So that's everything I had. I think we're pretty good on time, but hopefully that sort of revealed to folks some of the challenges and some of the things we're working at with respect to trying to engineer maps using imagery, and open to any questions from folks. Thanks. Yeah, how did that work? So basically the approach we've taken is we sort of have a human look at this scenario. Let's pretend it's an intersection with 4 stop signs. And we have them say, yes, there are 4 stop signs. Here's precisely where they're located. And sort of storing that information so that if you come at it blindly as an algorithm, if you produce 5 stop signs there, you've got a false positive. And that's the general idea. But it's really, I think the thing that sort of we've done that I think is cool about it is it's really just based on real data, and sort of it's based on the final result that we're trying to get to. So it's sort of a broader integration thing than just like a code module integration, or sorry, unit test.
Obviously, for active learning, you're trying to improve your lower performing classes, but even for the high performing, 99%, 9%, do you use any kind of confidence metric to help do human verification of the signs that you're particularly sure about, or less sure about?
Yes, we do actually. Yeah. So, it's not. Yeah, accuracy is sort of has multiple dimensions to it. There's a confidence direction too, and that's used. Yeah, just without more detail. Yeah. Cool. Yeah. And thanks to David for organizing this workshop.